Today our topic is logic equivalence. In order to understand what is meant by logic equivalence, we are going to look at two compound propositions constructed by two atomic propositions P and Q. Now P and Q are two atomic propositions, and now we are going to look at the first compound proposition constructed by P and Q, which is the negation of the conjunction P and Q. Okay, this is the first compound proposition constructed by using P and Q. The second compound proposition is the disjunction not P or not Q. Okay, this is the first one, which is the negation of P and Q. This is the disjunction not P or not Q. Now we are going to construct the truth table of this one and this one. Okay, that's what we are going to do. Since both these compound propositions are constructed by the same two atomic propositions, instead of creating two truth tables, we can include both these in the same truth table. Now this is what the truth table is going to be like. Now it has 1, 2, 3, 4, 5, 6, 7 columns. One for P, one for Q, one for not P, one for not Q, one for the conjunction P and Q, one for the negation of P and Q, and one for not P or not Q. Right, and it is going to have 4 rows. Now P and Q can have 4 different arrangements of truth values. Both can be true, both can be false. P can be true, Q can be false, P can be false, and Q can be true. Okay, now since this is true, not P is going to be false. Since this is true, not Q is going to be false. Since here P is false, not P is going to be true. Q is false, not Q is going to be true. Here P is true, this is false, then Q is false, not Q is true. Here it's the other way around. Since P is false, this will be true. Q is true, not Q is going to be false. Okay. Now we are considering the conjunction P and Q. Here P and Q both are true, this is going to be true. Both are false, this is going to be false. Mind you, this is a conjunction. Here only one is true, this is going to be false. Only one is true, this is going to be false. Now we are going to consider the negation of the conjunction. This is true, this will be false. This is false, this will be true. This is false, this is going to be true. This is false, this is going to be true. Okay. Now we are going to consider the disjunction of these two columns. Okay, not P or not Q. Both are false, this is going to be false. Both are true, this is going to be true. Here only not Q is true, that is sufficient to make the disjunction true. Here not P is true, that is enough to make the disjunction true. Now can you see something important, something very interesting, right? What is the truth value here? The first one, both are true. When both are true, truth value of this is false, this is also false. Here both are false. The truth value of this is true and this is also true. Here P is true, Q is false. Truth value of this is true, truth value of this is also true. Here P is false, Q is true. Truth value of this is true, truth value of this is also true. For each specific arrangement of truth values of its atomic propositions, the negation of P and Q and the disjunction not P or not Q have identical truth values. Identical truth values. Therefore, we say that not the negation of P and Q is equivalent to not P or not Q. This is what is meant by logic equivalence. So two compound propositions are logically equivalent if they share identical truth values in each occasion, in each arrangement of the truth values of its atomic propositions, right? Or we can say that two compound propositions are logically equivalent if they share identical truth values in every model. Okay, now here both are true, the truth value is the same. Both are false, it's the same. This one is true, this one is false, it's the same. This one is false, this one is true, it's the same. So they are equivalent. That is what is meant by logic equivalence. Okay, the next term is contradiction. Contradiction. A contradiction is a compound proposition, the truth value of which is always false. It is never true, whatever the arrangement of its atomic. Now, the reason why we must study logic equivalence is because they would give us better understanding of certain complex compound propositions, and also they would help us in proving certain mathematical arguments. Now this is why we must know something about these logically equivalent compound propositions. Okay, now before we study the types of logic equivalences, we need to know two important terms. The first one is tautology, the second one is a contradiction. Right? So first we are going to see what is meant by a tautology. Tautology. We are going to see what is meant by a tautology. A tautology is a compound proposition, the truth value of which is always true. Now we know that the compound proposition, it must be having several atomic propositions, right, from which it was constructed. Now whatever these the truth value arrangements of the atomic propositions is, the truth value of the a tautology is always going to be true, never false, right? Now we will look at an example. Consider this example: P or not P. Now, if P represents water is a liquid, then this can be read as water is a liquid or water is not a liquid. If P stands for Gauss was a mathematician, then this is Gauss was a mathematician or Gauss was not a mathematician. Okay, so we are going to see whether this is a tautology. We are going to construct the truth table. So P, we will have its negation not P, and the disjunction P or not P. Okay, so P can be true or false. Since P is true here, not P is going to be false. Since P is false, not P is going to be true. Now we are going to consider the disjunction P or not P. Well, this is the disjunction. Since P is true, this will make it true. Since not P is true, in this instance also it's going to be true. So you see, when P is true and not P is false, the disjunction is going to be true. When P is false and not P is going to be true, still the disjunction is going to be true. So whatever the arrangement of the truth values of its atomic propositions are, the truth value of this compound proposition is always going to be true. So this is a tautology. I hope you understand. propositions is, right, the truth value of the contradiction is always going to be false. We are going to look at this example. P and not P, which is a conjunction of P and its negation. If P is water is a liquid, then this is water is a liquid and water is not a liquid. If P stands for Gauss was a mathematician, then Gauss was a mathematician and Gauss was not a mathematician. Okay, so we are going to construct the truth table of this. P, not P, P and not P. Here can be true or false. Since this is true, this is going to be false. Since this is false, this is going to be true. So since this is a conjunction, because not P is false, this is going to be false. Here, because P is false, the conjunction is going to be false. So this is a contradiction. Okay, it's a contradiction. Now we are going to look at some important logic equivalences. First, we'll be considering equivalences involving negations, conjunctions and disjunctions. Now, since these compound propositions are not under the influence of a condition such as if then or if and only if, we call negations, conjunctions and disjunctions as non-conditional compound propositions. Now, there are 10 logic equivalences which involve non-conditional compound propositions. Okay, let P, Q, R be 3 atomic propositions and capital T be a tautology and capital F represents a contradiction. So the first type of logic equivalence is called identity. This is the first type, identity. There are 2 cases of identity equivalences. The first one is P and T is equivalent to P. The conjunction atomic proposition P and a tautology is always equivalent to the atomic proposition P. The second one is the disjunction P or a contradiction is equivalent to P. Okay, we will consider this one, right? So we are going to construct the truth table of this and see whether this left hand side of the equivalence has identical truth values to P. That's what we are going to see. Okay, so we are going to construct the truth table here. P, this column is for the contradiction and this column is for the disjunction P or F. Okay, now we know that P can be true or false. The contradiction is always false. Their disjunction, since P is true, this is going to be true. Here both are false, so this is going to be false. Well, now you can see that the disjunction has identical truth values as P. So this side is equivalent to this side. Okay, they have identical truth values. So this is the equivalence. It's called identity, right? Then we come to another type called domination. Domination. Again, there are 2 cases to consider. The first one is the conjunction P and F is equivalent to the contradiction. Second case is the disjunction P or a tautology is equivalent to the tautology. Okay. Now here you saw why it's called identity, because P and the conjunction with a tautology is equivalent to P. Now here is the other way around, because it just shows the dominating ability of a tautology or a contradiction. That is why it's called domination. The conjunction P and F is equivalent to F. The disjunction P or T is equivalent to T. That's why the equivalence is called domination. Now we will check this one, this equivalence. Here we have P, one column for F and another column for P and F. Okay. P can be true or false. The contradiction is always going to be false. Their conjunction, for this to be true, both of these got to be true, right? Here only P is true, so this is false. Here both are false, so anyway false. So the truth values of this and this are identical. So this side is equivalent to this side. So this equivalence is true. Okay. So we call that domination. The third one, the third type of equivalence is called double negation. Double negation. Double negation. Well, there's only one equivalence to consider here. The negation of not P is equivalent to P. This is common sense, right? If we are talking about the negation of some atomic proposition, then we consider the negation of that negation, then that is, again we are talking about the atomic proposition, right? It's like we say that Gauss was not a mathematician here. Then considering the negation of Gauss was not a mathematician, right? Then eventually we come to Gauss was a mathematician. You understand? We are talking about the negation of the negation that would actually result in the original atomic proposition. We are not going to construct the truth table for that. Okay. The fourth one, the fourth type is called idempotent. Now let's see what that term means. There are two cases. The first one is the conjunction P and P is equivalent to P. The second one is the disjunction P or P is equivalent to P. Now when you see that the conjunction and the disjunction, they have failed to construct a new proposition. It seems like they have lost their potential to construct a compound proposition, right? Now the conjunction P and P, it is equivalent to P. The conjunction P or P is again equivalent to P, right? So though this is a compound proposition, it seems, since the truth values are equivalent to P, it seems that they have lost their potential. So that is why it's called idempotent, right? So I'm not going to construct the truth table in for these two logic equivalences. Then we come to the fifth one. The fifth one is called commutative, which means they communicate on either side. So the two cases are, the first one, P or Q is equivalent to Q or P. Okay. Second one is P and Q is equivalent to Q and P. Now you can understand, even if we construct the truth table, this is the same thing. It's like we are just interchanging the columns, right? We first put P, then Q, then we consider P and Q. In the second one, we will first write Q and then P, and there we are considering Q and P. So whatever we do, it's not going to change, right? It is not going to have any effect. So we call that commutative. P or Q is equivalent to Q or P, and P and Q is equivalent to Q and P, right? So there's no need to construct the truth table in that occasion as well. The sixth one is called associative. Okay, the sixth one is called associative. Now again we have two cases. The first one is now consider this conjunction of the three atomic propositions. It doesn't matter if we perform this first and then consider the conjunction with P, right? Or we perform this side first and consider the conjunction with R. Okay, so here P and the conjunction Q and R is equivalent to P and Q, the conjunction P and Q and R, right? That's what the first one says. The second one is the same thing, almost the same thing. It doesn't matter if we perform this one first or this one first. Okay, it's the same thing. Here we first perform the disjunction Q or R, then we consider the disjunction P or Q or R. On this side, on the right side, we first perform the disjunction P or Q, then we perform the disjunction, or we consider the disjunction P or Q or R, right? So they are equivalent. Again, I'm not going to construct the truth table. I think it's easy to construct the truth table. The seventh type of logic equivalence is quite interesting. It's called distributive, right? There are two cases. P and Q or R is equivalent to P and Q or P and R. The second one is P or Q and R is equivalent to P or Q and P or R. You can see that this is totally different to the associative one, though there are three atomic propositions involved, right? Here the two operations are different. They are the exact opposite. Here we consider the conjunction, here we consider the disjunction, here we consider the disjunction, here we consider the conjunction, right? Why is this called the distributive property? If you can remember your basic algebra, we know that if A, B, C are three real numbers, right, then B plus C multiplied by A is equal to AB plus AC. This is something very similar to that, right? This is something very similar to that. So we just can't see whether as in the case of associative equivalence, it's not that easy to see whether these two sides are equivalent or they share the same truth values. So in order to see whether they share the same truth values, we must construct the truth table. So here we have 3 propositions. Now when we have 2 propositions, we need 4 rows, right? 4 rows. Because there are 4 possible different arrangements. 4 possible different arrangements of the truth values of P and Q. But when it comes to 3 atomic propositions, we need 8. We need 2 to the power 3 number of atomic propositions. How we got this number? Well, if you know basic counting, I'm not going to talk about basic counting here. There is a thing called permutations, right? We consider all the possible arrangements, not combinations, all the possible arrangements. Now here we have 2 choices, true and false, and we have to consider these choices on 3 different occasions where any of these choice can be repeated. So this is the number of rows that we are going to get if we construct a truth table for a compound proposition that involves 3 atomic propositions. Okay, when you understand the permutations, you will see why. Instead of creating a truth table for the left hand side and another one for the right hand side, we have included both these compound propositions in this truth table because they involve the same atomic propositions. Okay, now as we said earlier, right, it's going to have 8 rows. So to save time, I have written down here all the possible different arrangements of truth values of these 3 propositions. There's going to be 8 different arrangements. Okay, so now we are going to see what is the truth value of Q or R is going to be. Q or R, this is Q, this is R. So here this is both are true, this is true. Okay, both are false, this is false. One is true, that makes it true. Here R is true, this is true. Both true, true, true. Here both false, this is false. Okay, now we are considering the conjunction of this P and this. Okay, so here both are true, it's true. Now for the conjunction to be true, both P and Q are got to be true. Let's see on what occasions that happens. Here it is both true, this is true, and here it is both true, again it's going to be true. Okay, and that's all, right? In all the other occasions it's going to be false, 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 right? Okay, yes. Okay, now we are considering the conjunction P and Q. P and Q. This is true. The third one is true. That's all. Yeah. On all the other occasions, it's going to be false. Now we are going to consider P and R. This is true. The fourth one is also true. All the other occasions is going to be false. Okay, now we are going to consider the disjunction of this and this. Since it's a disjunction, this is true, this is false because both are false. True, right? True, false, false, false. Okay, now we have completed the truth table. Now look here, in the first arrangement, P is true, Q is true, R is true. the truth value of this is true, the truth value of this is also true. These are the two rows that finally matter. They tally. Here all three are false. Okay, truth value of this is false, truth value of this is also false. They tally. The third instance, these two are true, this is false. Okay, truth value of this is true, truth value of this is also true. They tally. Here TFT, true, false, true. This is true, this is true, they tally. Here true, false, true. We have already considered that. Here false, true, true. Truth value of this is false, truth value of this is also false. They tally. Here false, false, true. Truth value of this is false, truth value of this is also false. They tally. The final one, true, false, false, is the arrangement. Truth value of this is false and truth value of this is also false. They also tally. So you see, in every different arrangements of the truth values of the three atomic propositions, the truth value of P and Q or R and the truth value of P and Q or P and R is identical. Therefore, the first equivalence holds. We can construct the same thing for a similar truth table for the second one as well and prove that that equivalence also holds. Number 8 is named after the famous British one-eyed mathematician and logician Augustus De Morgan. So we call these equivalences De Morgan equivalences. There are two instances. The first one is the negation of P and Q is equivalent to not P or not Q. The negation of P and Q is equivalent to not P or not Q. The second one is the negation of P or Q is equivalent to not P and not Q. Okay, these are the two De Morgan equivalences. We'll be revisiting the De Morgan equivalences when we study set theory. Now I think this was the example that we used to understand what is meant by logic equivalence. So there's no need to prove this one. So if you are interested, you can construct the truth table for this. The ninth one is called negation. Again, there are two instances. P and not P is equivalent to a contradiction. P and not P is equivalent to a contradiction. Number 2 is P or not P is equivalent to a tautology. I think when explaining what is a contradiction and what is a tautology, we use both these examples. We constructed the truth table of both these instances, right? The 10th one is called absorption. Again, there are two instances to consider. First one is P and P or Q is equivalent to P. Second one is P or P and Q is equivalent to P. Okay, so if you want, you can construct the truth table and see whether these equivalences they are true. Okay, now these are the 10 logic equivalences involving non-conditional compound propositions. Now we come to the logic equivalences involving conditional compound propositions, or the we'd be considering the unidirectional implications and the bidirectional implications. There are several such equivalences, but we'd be studying only one under the unidirectional implications and two under bidirectional implications, because our aim is not to study logic but to study mathematics. Okay, so under the unidirectional implications, this is the equivalence that we must know. P implies Q is equivalent to not Q implies not P. This is very important because this is the basis of a method of proof called proof by contraposition, right? Now this we are going to construct the truth tables of the left hand side and the right hand side and see whether this holds. This is the truth table. Now we are going to see where the truth value of this side is identical to the truth value of this side in each different arrangements of the truth values of both P and Q. Now what are the four different arrangements? Both can be true, both can be false, P can be true, Q can be false, P can be false and Q can be true. Next we are going to fill in the blanks of this column, not P. Since here P is true, this is false, this is true, this is false, this is true. Next, not Q, this is true, this is false, this is false, this is true, this is false, this is true, this is true, this is false. Then we have to consider P implies Q. P implies Q is going to be false only when P is true and Q is false. So only in the third instance, right, third scenario, this is going to happen, right, when P is true and Q is false. In all the other instances, this is true. Here it is true, here it is true by default, here also it's true by default. Now finally we have to fill in the blanks of this column which represents not Q implies not P. Not Q implies not P. Here it is true by default, here it is true, here it is false because this is true, this is false. Here it is false, this is true by default. Now there are four possible arrangements of truth values. When both are true, this is true and this is also true. They tally. When both are false, this is true again, they tally. When P is true and Q is false, this is false, they tally. Finally, when P is false and Q is true, this is true and this is true, they tally. Therefore, in every different arrangement of the truth values of their component propositions, the truth values of P implies Q and not Q implies not P is the same, right? So this equivalent holds. This is very important, you have to know this. Then we come to the two equivalences that we must know under the bidirectional implications. The first one is P if and only if Q is equivalent to P implies Q. We already know this, okay, and Q implies P, right? We already know this. If you are interested, you can construct the truth table and prove this. Okay, this is the first one. The second one is P if and only if Q is equivalent to not Q if and only if not P. Okay, this is the second one that you should know. Again, you can construct the truth table and check whether these two compound propositions are equivalent. In summary, we first studied the meaning of logic equivalence. Then we studied two terms, tautology and contradiction. Then altogether we studied 13 different types of logic equivalences. 10 of those involved non-conditional compound propositions and 3 involving conditional compound propositions. Okay, so that is the summary of what we have studied so far. With that, I come to the conclusion of the video. Thank you for watching.